Hola. Okay, time to do some some discrete math. In particular, we were talking about random variables last time, and in particular, we were interested in uh, the variety of random variables that were of the discrete type. We were working on two specific examples, namely the example where we have a coin that we're flipping, and I think we flipped it 10 times, and we wanted to know the expected number of heads, right? Eventually we'll actually have a more general version of that problem that we'll be interested in. But one reason I wanted to go through that example in gory detail was because I wanted to sharpen your skills a little bit when it comes to manipulating sums. That's just part of the nature of the beast. When one works in probability and statistics, you oftentimes end up having to simplify sums and remember how to do those sorts of things. So that's what we did. And we had another situation that was the rolling of two die and looking at the sum on those two die. So I want to start with that. Okay. So find the expected value of the number of heads in 10 flips of the coin. Okay. Expected value. Now remember, the expected value. Oh, sorry. Yeah. Excuse me. That's what we ended with last time. Okay. We did that problem in a lot of detail. But remember, the expected value is gotten at by simply taking all the outcomes and multiplying them by the probability that they occur, and then adding those together. It's like a weighted, W-E-I-G-H-T-E-D, weighted average of all the outcomes of the random variable in question. Okay? So this is the one I wanted to start with. Find the expected value of the sum of two dice, the sum of two dice. Okay? So let's see here. Let's go to Wolfram Alpha. Okay, and I'll remind you as we're doing this computation how it is that we are able to find the probabilities of certain things. So what are the values for the sum of two die? What are the values of the sum of two die? Okay. Well, 2, 3, 4, all the way up to 12, yes? So we want to take those values and multiply them by the probabilities that they occur and add the results together. So it'd be like 2 times, okay, what is the probability that two die will roll to give us 2, a sum of 2? Well, there's one way that can happen. That is, you do a 1, 1 out of 6 times 6 or 36 total rolls of the die, right? Any of 6 options can go with any of 6 options from the first and second die. So 6 times 6 is 36. This is 1 over 36, okay, plus, okay, what about 3? How many ways can we get a sum of 3? Well, 1, 2, or 2, 1, okay? 1, 2, or 2, 1. So it's 2 out of 36, okay? Plus 4 times 3 out of 36, if you think about it. So how many ways are there to get a 4? 1, 3, 2, 2, 3, 1. Okay, 3 out of 36. And this pattern is going to continue. 1, 2, 3. Okay, so for a sum of 5, it's 4 out of 36. For a sum of 6, it is what? 5 out of 36. Okay. And for a sum of 7, and by the way, we had a table in our slides that actually did this in full detail. For 7, it was 6 out of 36, okay, plus 8, and this is where things get interesting, because the reason you had so many options for 7 is 1 plus 6. Okay, so I go, as low and as high as I want on the die, but now there's some restrictions. Okay, for 8, how am I going to get an 8? Well, 2 and 6, right? So I kind of have to start 1 up from where I did with the 7, like 2 and 6, and then I kind of go down and they cross each other, and 6 and 2 is the last one. So I'm gonna actually start decreasing now. So that's 5 out of 36, okay, plus 9 times 4 out of 36, right? That one's gonna decrease by 1 more, plus 10 times 3 out of 36, plus 11 times 2 out of 36, right? How many ways are there to get an 11? Well, 5, 6, or 6, 5. Okay, 2 out of 36. And then finally, how many ways are there to get a sum of 12? Well, 1, 6 and 6. Okay, and before I hit enter, well, it's already giving us the answer here. It's 7. Look, this is perfectly symmetrical. 1, 2, 3, 4, 5, 6 out of 36. 5, 4, 3, 2, 1. You would expect, since it's a nice like symmetrical distribution, that the average would be right in the middle. Okay, so 2, 3, 4, 5, 6. There's 5 numbers on the one side of 7. 8, 9, 10, 11, 12. There's 5 numbers on the other side. 7's right in the middle. So it makes sense that this would be perfectly in the middle. Okay, so 7 is the expected value of this thing. Okay, 7. All right, so let us go back to the slideshow here. Okay, and let's just go from current slide. Okay, so we did that. Okay, so let's talk about some common discrete PDFs. Okay, remember what a PDF is? That's called the probability distribution function, or even sometimes even the word density is used. Also, PMF for probability mass function is fairly common terminology. Okay, we're going to talk about all of these. Okay, we're probably going to spend not much time on the hypergeometric, but we'll talk about the binomial, the geometric, and the Poisson. The Poisson. Okay. Those are some important ones. The Poisson especially is important when you're dealing with queuing theory. Okay, queuing theory in applications in theoretical computer science. The Poisson random variable comes up and things that are related to it. Okay, but the binomial and the geometric, I think you'll kind of see fairly easily why those tend to come up quite often in practice as well. Okay. So discrete PDFs, okay, so these discrete PDFs, we try to match experimental situations with one of these patterns since we already know so much about them. Okay, so I said binomial, geometric, hypergeometric, Poisson. We're only going to talk about a handful of these, but if you knew them all, you would kind of look at a given situation you find yourself in and you would try to identify, oh, this is really just the binomial experiment in disguise, okay? And so that's what we're always trying to do. So let's look at the binomial experiment. What in the world is it? Well, here what we're doing is we're just executing some number of trials of an experiment over and over and over again. And each trial is independent of any other trial. So there's n total trials. They're independent and identical. Okay, we often call these Bernoulli trials, if you look down there at the bottom of the slide, named for the famous mathematician Jakob Bernoulli. Jakob and Johann were probably the most prominent of the Bernoulli brothers. I think it was Johann that was actually the legitimate discoverer of L'Hopital's rule, but he was a benefactor for L'Hopital, Marquis de L'Hopital at the time, and kind of bought his own. The Marquis de L'Hopital actually bought his name onto that theorem because, you know, these Bernoulli brothers, what need did they have to have their names on anything else? So it's pretty widely known that L'Hopital's rule should have the name Bernoulli attached to it as opposed to L'Hopital, okay? But back to this binomial experiment. Each of those independent trials is called a Bernoulli experiment. Okay, each trial is either a success or a failure. There's just one of two outcomes. It's either successful or it's a failure. So you can almost imagine like a coin flipping situation might be like this. You might consider heads to be a success, for instance, and tails to be a failure. Okay, you denote the probability of success by P and the probability of failure by Q. Okay, and of course, since there's only two options here, either success or failure, P plus Q is necessarily equal to 1, like 100%. So in the coin flipping case, you know, if my success was heads, then P would be a half, but so would Q, right? Q would be the probability of failure or getting a tail in that case. Or like if I'm rolling a die, for instance, and I'm keeping track of the number of times I roll a 1 or a 6. Every time I play Trouble with my kids, you know, we're always obsessed with rolling a 1 or a 6. Okay, so that's definitely a success in Trouble. So the probability, and there it's like I roll the die, I get a 1 or a 6. There are 6 possible outcomes. It's one die, okay? What is the probability of success? If success to me is, you know, get a 1 or a 6, well, 2 out of 6 or a third. And then of course the probability of failure would be 2/3 in that case, okay? And in the binomial experiment, we're just doing that some fixed number of times. N could be anything, could be 100, you know, but I know ahead of time, the number of trials that we're going to execute, okay? What I don't know is how many successes I'm going to have. So if I perform the experiment N equal to 100 times, what I don't know is how many successes I'm going to have. So that would be what is random. That would be the random element in this experiment, the number of successes, okay? So that's why we define the binomial distribution this way, okay? X is just the number of successes in these N independent Bernoulli trials. The notation we use is X, and we put that little twiddle symbol, tilde. That means X is distributed as B for binomial. N is the fixed number of trials that you're doing for those independent Bernoulli trials, and P is the probability of success. So in the coin flipping problem, we were flipping the coin 10 times. So N was 10. And what was our P? There we were keeping track of heads, right? So X was like the number of heads, right? Which is the number of successes in that case. And the probability of success was 1/2 in that case. And what was our mean, mu? Well, after all that computation, we discovered it was 10 times 1/2. And in general, that's what happens. The mean is just the number of trials times the proportion of success, right? So that's like the expected number of successes. This should be intuitively clear. The expected number of successes is just the number of times you did the experiment times the proportion of success, okay? And then the variance, okay, the variance for this thing is, well, N times P times Q. So the standard deviation is the square root of that, okay? I believe we kind of talked about, is that back here somewhere? I think, hopefully, well, maybe not quite yet. The variance, I haven't really talked about that too much. I talked about the expected value. The variance basically is a measure of how far the random variable deviates from the mean. Okay, it's an average deviation from the mean. And in this case, that's why it's a standard deviation. So like the mean is the one number summary for the random variable. If I had to like give you a one number summary for the random variable, that's what I would tell you. I would say, okay, the mean number of heads is 5 if I flip a coin 10 times, and the proportion of success is 1/2 for heads. but that doesn't necessarily mean that that's a likely value for the number of heads, okay? That doesn't mean it's necessarily a likely value. And the standard deviation is what keeps you, is what sort of tells you, okay, how good is the mean predicting the overall behavior of the thing? If the standard deviation is big, that means that the random variable's fluctuating like mad around the mean. It's not really staying close to the mean at all. But if the standard or the average deviation is small, that means this thing is not fluctuating that much away from the mean. Okay, so that's kind of the meaning of that standard deviation thing. Can you think of any examples? Well, I kind of gave you one, namely, if I roll a die, if I'm playing trouble with my kids and I roll a die, I might consider like one die, I might consider rolling a 1 or a 6 as being a success. Then the proportion of success would be 1/3. And maybe I would be curious to know, okay, if I roll the die 100 times, remember in the binomial case, I have to know the number of trials that are being executed. Okay, so maybe on 100 times, I want to know how many successes I have. That is, how many 1s or 6s do I actually get? The expected number is going to be 100 times 1/3, okay, which is not an integer. That's 33 1/3, but that's how this that sort of is intuitively clear why it would be 100 times the proportion of success. Okay. Here's one. X is equal to the number of heads and 10 flips of a coin, right? We already talked about why that's an example of a binomial distribution. And here is the formula for this thing. And this thing might look a little bit mysterious, but it shouldn't if you remember what we did in the case of the coin flipping problem. Okay, and I think I'm gonna I'm gonna go over here and actually explain this formula right here. Okay, so here we go. Okay, we get into our whiteboard here, just a second. Here we go. Okay, here's this. So let me just remind you of some stuff that we did last time. We actually found, let me see, where is this? Here it is. Here it is right here. Okay. So if X is the number of heads in 10 flips, then what I'm saying is this thing is distributed as, right? It's distributed as binomial with what's n? So n is 10. And what is P? Proportion of success is 1/2. Okay. So that's a binomial with n equal to 10 and P equal to 1/2. And remember, we came up with this probability mass function for this thing. Okay. And where did it come from? Well, we said, okay, a probability of little x, where little x is the number of heads. Well, in the sequence of 10 coin flips, I need to choose X places in which to put heads. The other ones are going to be tails. And, each of those occurs with the same probability, 1/2 to the 10th, right? So this 10 choose X was the number of X head sequences. Okay, it was the number of X head sequences. Okay, of course, there's going to be 10 minus X tails in there. And each of those occurred with the same probability. Okay, each of those occurred with the same probability, namely 1/2 to the 10th. So that's where that probability mass function came from. Well, okay, let's think about, oh man, this thing is filled up. Let's go to the last page here. So what about the probability? So if X is distributed as binomial with n trials in proportion of success, P, what is P of little x, right? Where this is, again, the probability that x is equal to little x. And what are the possibilities for little x? Let's think about that for a minute. I could have 0 successes. Remember, x is the number of successes, right? So it's the number of successes in trials. Okay, so it's the number of successes in n trials. Okay, so what are the possibilities? Well, I could have 0, and I could have all the way up to n possible things. So this computation is going to be almost the same as that other one. First of all, I need to figure out the number of x success and n minus x failure sequences. Well, that's just n choose x. Okay, so this right here is the number of x success and n minus x failure sequences. Okay, sequences. And each of those is going to occur with the same probability because like the trials are all independent. So I just have to go, okay, in those x successful slots, the probability of success is p, right? There's x of those. So it's going to be times, so p to the x. Okay, so each of those x successes occurs with probability p. And what about the failures? Those occur with probability p or probability q. And there are n minus x of those things multiplied together. So by the way, another way to write this is just, if you don't want to write q has to be 1 minus p because there was only the success and failure in this case. So it's p to the x times 1 minus p to the n minus x. Oh man, hang on a sec. We're running out of room over here. N minus x. Okay, so there you go. So there is the distribution, the probability distribution function or the density function, whatever you want to call that. Okay, so let's go back over here. Here it is. Back to the presentation. That's where this formula comes from. The probability of x equaling any particular k is n choose k, p to the k, times 1 minus p to the n minus k. Okay, that's good. All right, moving on. Oops, sorry. Okay, the Poisson distribution. Okay, so I'm covering this one next because it comes up so often in computer science applications. So I want to make sure you have a pretty firm grasp of what's going on with that one. Okay, so in a Poisson distribution, what's happening is events are kind of happening independently, and so an event that I care about, like for instance, I'm sitting at an intersection and I'm watching cars go by, and I'm a traffic engineer and I just want to know how many cars are going to pass me as I sit on this street corner in one over the period of one day or something. Okay, so cars kind of travel past me independently of one another and at a known average rate. So I would just kind of collect data for a while until I had an average rate per time unit interval in my grasp. Okay, so what's weird is with the Poisson distribution, you sort of know the average before you even know the distribution at all, before you know the actual probabilities themselves. You collect data and you know the average first, okay? So here's some examples. Average number of bad checks a certain bank receives per day is 6, okay? So I don't know that I'm always going to have 6 bad checks in a given day. That's just the average. The distribution of the number of bad checks I'm going to get in a random day has the Poisson distribution. So I have a known average rate, and I'm just counting the number of observations that happen in my window of observation. Average number of times a reporter says or maybe the number of times I say in these in these videos during a 6-minute show is 2. Wow, that's impressive. Okay. So there it's like you have a 6-minute show and you're just counting the number of times a reporter says Does that mean that you know that every time there's a 6-minute show there's going to be 2 ums that are said? No, I mean that's the average number. So you give me a random 6-minute show, and it is going to be a random amount of times that a reporter says the word during that 6-minute show. Okay, so that's a random variable. Okay, so X is defined to be the number of occurrences in the interval of time or space. Okay, so incidentally, I mean, like I said, you know, you don't have to be talking about time necessarily. You might actually be sitting at a conveyor belt, you know, and looking for the number of flaws every 100 feet of plywood or something that you look at. Okay, so it could have something to do with geometric space as well, but you're just counting the number of occurrences. That is a random variable. Lambda is the mean number for the interval of interest. Okay, lambda is the mean number, and so the average number. So you already know the average ahead of time before you even have the distribution. You have the average, and you say that X is distributed as the Poisson random variable with parameter lambda. Okay, so lambda is the mean that's given to you on the front end. Okay. Okay, so here's an example. X is the number of typos in 100 pages. If it's known that on average there are 2 typos in a page. Okay, so this would have okay, so what would, okay, so 2 typos in 100 pages. So X is going to have the Poisson distribution with parameter 2. Okay, I would assume that this is like some kind of, you know, very carefully edited 100 pages that only have that many typos on average per 100 pages. Okay, but do we always know that there's going to be exactly 2 typos? Well, no, that's the average. X is a random variable counting the random number of typos for a random collection of 100 pages. Okay. Poisson can be used to approximate the binomial if the probability of success is small and the number of trials is large. Now remember, lambda was the expected number of observations. Okay, so lambda is the expected value of this thing. So if I'm going to use this to approximate the binomial, because computationally the Poisson is usually pretty easy to compute probabilities for, whereas the binomial is complicated because you have all those. I mean, you guys saw what we were doing. I had to write all those sums, and it was crazy. Yeah. Now the Poisson also has sums, but it also has some fairly nice approximations that are automatically available to us that the binomial doesn't have. So the expected value for the binomial was the number of trials times the proportion of success, n times p. The expected value for the Poisson is lambda. So whenever we want to approximate the binomial with the Poisson, our lambda has to be equal to n times p. Okay. And here is I'm not going to explain this formula because it involves some pretty high caliber calculus. But, oh, and again, I have to reiterate, the probability of success has to be really small and the number of trials has to be really large. to use this approximation. Okay, so really tiny probability, really big number of trials. Then you might as well be using the Poisson with lambda equal to NP. Okay, and here is the probability of x being equal to some number if we're in the Poisson distribution. And x is a non-negative integer here because in theory I could observe 0 things, but I could also observe 1 or 2. And in theory, there's really no limit to the number of observations that might happen in my interval of interest. Okay. But the probability that x is equal to k is given by this formula. It's lambda to the k, e to the minus lambda over k factorial. I'm not going to explain that. It has to do with some calculus limits, but there it is. Okay, the probability that x is k is given by that. Example, 6 different colored dice are rolled. Of interest is the number of dice that show a 1. Okay, number of dice that show a 1. Okay, so 6 different colored dice. 6 different colored dice are rolled. So I don't know, red, orange, yellow, green, blue, purple. Okay, that's 6 colors. That would be a rainbow of colors for sure. Of interest is the number of dice that show a 1. Okay, so this sounds like, let's not get totally sucked into the, let's not totally get sucked into necessarily assuming that this is Poisson just yet. Essentially, you have 6 independent trials. Okay, and what's the probability of success for each one of these? Okay, the probability of success, right? Success here means roll a 1. Okay, so what is the distribution going to be? Well, binomial with n equal to 6. I have 6 individual experiments I'm doing with these 6 colored die. And the proportion of success is 1/6. Okay, so x is going to be the number of dice that show a 1. I'm doing the trial 6 times, proportion of success 1/6. Okay, so define an appropriate x. So x would be binomial with n equal to 6, p equal to 1/6. What are the values that x may have? This kind of would have given away, that it actually was not Poisson, because Poisson, you can take on 0, and in theory, you could have any number of, any positive integer or non-negative integer number of observations. Okay, but binomial, you have an upper limit. Okay, and here the values are either 0 or 1 or 2 or 3 or 4 or 5 or 6. And the distribution, of course, is binomial. N equal to 6, p equal to 1/6. And what's the expected value for this thing? Well, it's the number of trials times the proportion of success. 6 times a 6th is 1. That kind of makes sense. I expect, on average, that about 1 of these is going to be showing a 1. Okay, so that sort of makes sense to us, hopefully. Okay. Find the probability that all 6 dice show a 1. Okay, and find the probability that 3 dice show a 1. Okay, I want the probability that all 6 show a 1 and the probability that 3 dice show a 1. Okay, so I'm gonna go over here into the into my iPad so we can do a little bit of computation. Okay, here we go. Let's see here. Here's our board. Okay, we already determined that this thing was the binomial distribution. Okay, so let's let's keep going here. Need another page. Okay, so x was equal to the number of ones in 6 die rolls. Okay, and we determined that x was binomial with n equal to 6 and proportion of success equal to 1/6. Okay, and let me write this. X belongs to, of course, 0, 1, okay, all the way up through 6. These are the possible outcomes for this thing, okay? What did I say? I wanted the probability. Okay, let me take a peek here just to make sure. I wanted the probability that all 6 dice show a 1. I wanted the probability that all 6 dice show a 1. And I wanted to find the probability that 3 dice show a 1. Okay? Okay, probability that all 6 dice show a 1. So that would be the probability that, okay, all 6 dice show a 1. What would that be? Well, all 6 dice show a 1. It's probability that we have all 6 being successes. So probability that x is equal to 6. And the other one that we wanted to compute was the probability that 3 dice show a 1. So all 6 show a 1, and the probability that all 3 show a 1. Okay, so we also want, so this is equal to what? And we also want the probability that x is equal to 3. What is that? Okay, well, we can just straight use the formula for these things. And we could actually, here it kind of makes sense what it's going to be. So the probability that x is equal to 6, remember the formula said you go 6 choose whatever that number is, 6 choose 6, okay, times the probability of success raised to the 6th, okay, or raised to the 6th power, 1/6 to the 6, and times the probability of failure raised to the 6 minus 6. Okay, so I mean this is kind of easy. 6 choose 6, that's just 1. It's going to be 1/6 to the 6th and 5/6 to the 0. So this just ends up being 1/6 to the 6th power. But that's just sort of clear that that should be the answer, because each die would have to show a 1. What's the probability that the first die shows a 1? A 6th. The second, a 6th. And you just multiply those 6 factors of 1/6 together. What about the probability that x is 3? Well, that would be 6 choose 3. 1/6, right? Because I have to choose 3 places in which to put a success in the sequence of rolls. There are 6 rolls that are happening, okay, in the sequence of rolls. And I have to choose 3 of them to be successful, that is to have a 1. That's going to be 1/6 to the 3rd times 5/6 to the 6 minus 3. Okay, because the powers on these things always have to add up to the total number of trials, and that's 6 in this case. Okay, so so that's just 6 choose 3. I'm just going to kind of leave it like this. 6 choose 3. Really, the whole, so this is 1/6 times 5/6. Let me just write this as 5/36, all raised to the 3rd power. Okay, right. I just took the 1/6 and 5/6 and multiplied them together. Since they were both under the power 3, I can do that in this case. So that just makes it easier to compute later on, okay? So let's go back to the presentation here, okay? Yeah. Okay, so from current slide. There we go. Okay, back in here, probability that 3 dice show a 1. Okay, now example 2. X is the number of typos in 100 pages, where on average there are 2 typos in 100 pages. What is the distribution of X? Well, it's the Poisson distribution. So number of typos in 100 pages, average of 2 typos per page. It's going to be the Poisson distribution with parameter lambda equal to 2. It's going to be the Poisson distribution with parameter lambda equal to 2, okay? Okay. All right. So let's think about that for a minute, okay? The book needs to be edited again if there are more than 4 typos in the first 100 pages. Okay, so just think about that for a minute. Okay? If there are more than 400 typos in the first 100 pages. Okay, so x is going to be the number of typos, which is going to have the Poisson distribution with lambda equal to. What is the probability that this will occur? Okay. Okay, what is the probability this will occur? So if there are strictly more than 4 typos, okay, strictly more than 4 typos, okay, 5 or more, okay, and then lastly, what is the probability that there will be more than 400 typos in the first, or more than 4 typos in the first 200 pages? In the first 200 pages, okay? Well, there, what you have to do is you basically have to kind of have to redo the problem with another Poisson, okay? So if every 100 pages there were 2 typos, then what do you expect for 200 pages? Well, 4 typos, okay? So that's going to be a different distribution, okay? That's going to be, it's still going to be the Poisson, but it's going to be with a different parameter, lambda equal to 4, okay? Because that's going to be the number of typos in the first 200 pages, okay? Okay, so yeah. So that says, what is the probability there will be more than 4 typos in the first 200 pages? So that's the probability that random variable is bigger than 4, that other Poisson one. Okay, so I'm going to share this screen that I've kind of been taking a couple of notes here for us to look at together. So here we go. We'll do these couple of problems, okay? Okay, so here we go. Yeah. Go over here. Okay, so the first thing was the probability that this thing is going to need to be edited again is if x is bigger than 4, where x has the Poisson distribution with parameter lambda equal to 2. The other one was, okay, what's the probability you have more than 4 typos in 200 pages? Well, if we had 2 typos per 100 pages, then on average we'll have 4 typos every 200 pages. So that's a new Poisson random variable. And I want these 2 probabilities. That's what we were being asked to compute. Okay, well, how in the world do we compute these things? How in the world do we compute these? Well, it turns out we can. Okay, we can do it in Excel. Okay, so let's look in Excel here. Okay, so here we go. Let me put a new sheet in here. Okay. Okay, so x, so this is the first time we've kind of done any computation in here, so I want to be careful. So x is distributed as Poisson with lambda equal to 2. I'll put L equal to 2. Okay. Then what is the probability that x is greater than 4? Okay. What is the probability that x is greater than 4? Wasn't that going to be 1 minus the probability that x is less than or equal to? So x greater than 4, that's going to be 1 minus the probability that x is less than or equal to 4, isn't it? Okay, and actually we can use Excel to help us compute that. This is going to be equal to 1 minus, and what you do is you just start typing what you think the distribution is that you want. Okay, and in this case, it's the Poisson. So you start typing POI, and you see Poisson distribution. Okay, and what's the x value that we're interested in here? Well, x equal to 4. I want to go all the way up to 4. Okay, what is the mean for this thing? Well, it's 2. And cumulative means, okay, do you want me to add up all the probabilities up to this value 4? And the answer is yes. In this case, we do. Right? That's called the cumulative distribution function. And we actually want all the probability up to and including 4. Right? So you can either select true, or you can do like a binary with 0 false and 1 true. So I'll just put 1 in here, okay? I want to add up all the probabilities. That's why it's saying cumulative. If I would say false, it would just tell me the individual value of this thing, okay? Okay, and I get that. Okay, so that means there's about a 5%, 5.3% chance that this thing's going to have to be edited again. The other problem we were going to do was y distributed as Poisson. What was the lambda in this case? So lambda was 4 because this was a 200-page situation. And we wanted the probability that y was greater than 4, more than 4, okay, which, by the way, is 1 minus the probability that y is less than or equal to 4, okay? What is that? I'm just writing that as a label so that you can see what we're doing here. And now I'm going to let Excel do the computation. By the way, the reason that I kind of flipped this thing around in this way is so that I could use that cumulative feature that is built into Excel. So this is equals 1 minus Poisson. Anytime you want to invoke a function in Excel, you type equals and start doing some stuff. Okay, so it's Poisson distribution parameter or x value 4. What is our parameter this time? We were doing a 200-page block. There's going to be an average of 4. So the mean is 4 here. In cumulative, do I want all the probability added up? 0, 1, 2, 3, and 4? Do I want to add them all together, or do I just want 4? Well, I want them all. Okay, because it's y equal to or less than that. Okay, I hit enter, and I get 37%. There's a 37% chance that that happens. Okay, 37% that y is bigger than its mean. But the reason the other one is a lot smaller is x bigger than 4. Well, 4 is already way past its mean. The mean was 2. 4 is way past that, and we're asking for the probability it's even further beyond that. That's only a 5% chance. But here, we're just asking for the probability that y is actually bigger than its average, 4. And that not surprisingly is much, much bigger. Okay, so back to our presentation. There we go. Okay. I think I'm going to stop right now because I think this is probably getting pretty long. We'll stop right there. We've done an example of a binomial. We've done an example of a Poisson. And there's going to be a few more examples that we're going to do. A couple more examples that we'll do next time that will close out the section on Poisson and binomial. And then we'll get into the geometric. And we'll be ready to jump into the distributions of a continuous variety. Okay, I think that is going to be it for now. Bye.